This is second lecture in 204 on review of DC models of bipolar junction transistor as we started the last time, and we will also discuss a little bit about field effect transistors. I wish all of you a happy new year, and the rhyme, if you wonder, is as per my desire. Well, we were talking about the NPN transistor BJT. This is the emitter, this is the collector, and this is the base. The base, as you know, is a very thin region, and normally in the active region the emitter base junction is forward biased, which means that the emitter is connected to a negative terminal and the base to the positive terminal. This is the forward biasing, and the collector base junction is reverse biased, which means that this is negative and this is positive. The conduction mechanism is that the emitter injects electrons into the N region, most of which pass into the P region, and because the P region is thin, the electrons cross over to the N region, and these electrons are then collected by the positive potential of the battery. This is the basic operation of an NPN transistor, where the electrons are majority carriers here, electrons are minority carriers here, and this here also the electrons are majority carriers. As I told you, the emitter current which flows in this direction, let us call it I sub E, let us call it small I subscript capital E. I'll explain the notations in a minute. The emitter current consists of electron current as well as hole current, because there are holes which are minority carriers here. Now therefore the electrons that are injected into the P region will only form a part of the total emitter current. So if we define this ratio as electron current injected into the base, electron current injected into the base divided by total emitter current, this ratio is called the emitter efficiency and is denoted by gamma. This ratio usually it is very close to unity. 0.999 is a typical figure. For a good transistor, 0.999 is a typical figure. The reason is that the holes are in minority, okay, and therefore the hole current is negligible compared to the electron current, and most of the current that enters into the P region is the electron current. This is the emitter efficiency, and then the electrons which are injected into the base, not all of them can cross. Some of them will combine with the majority carriers which are holes in the P region. Okay. Some of the electrons injected from here will combine with the holes in the P region, and this combination, this recombination appears as the base current I sub B, the base current. Normally if there was no recombination, then the base current should have been 0, but since there is a recombination excuse me, that is a base current. Okay. So some of the electrons which are injected into the base region, they recombine with holes, and therefore the number of electrons reaching the collector will be less than the number of electrons emitted from the emitter region. If this ratio called the BTF, base transport factor, is defined as number of electrons reaching the collector divided by the number of electrons emitted into the base, This ratio, number of electrons reaching the collector divided by number of electrons emitted into the base, this ratio is called the base transport factor, and this is also very close to unity, maybe 0.99 is a typical figure, because the base current normally is very small. The reason being that the time that these electrons get to recombine with holes is very little. Very little time is available, because they have to respond to the call of the positive potential of the collector. All right. So they are forced. It's like a flood which crosses this barrier. Some of them are left behind to be eaten up by the holes into the form of a base current. Okay. So this base transport factor is also approximately equal to 1. And then the collector current, which is the direction of flow of positive charges, naturally shall be in this direction. And you can see that normally if IB is equal to 0, then the collector current should be equal to the emitter current. All right. But because of IB and because of this ratio, because of holes also contributing to conduction, I sub C, the collector current, is slightly less than the emitter current, and the exact relationship is that I sub C, the collector current, let me change this slide. The collector current I sub C is a fraction of the emitter current, alpha I sub E, where alpha is the product of, there are two reasons contributing to this constant alpha. It is the product of emitter efficiency and the base transport factor, and alpha in practice also is very close to unity, because both these factors are close to unity, and typical figure is 0.98, let's say. 0.98 is not a very good transistor, it's more than 0.98, okay, maybe 0.985. All right. Now the question is this the only current that flows into the collector? Now you must realize that a collector base junction is a reverse biased junction, and in a reverse biased junction there is a current called the reverse saturation current, and therefore the total collector current shall consist of not only the current due to the electrons emitted from the emitter, but also the reverse saturation current, which we indicate by I sub CO. This is the reverse saturation current in the reverse biased collector base junction. Okay. So this is the current relationship. I sub C, the collector current, is equal to alpha IE plus I sub CO. As a matter of notations, let me clarify why I put these notations. What we will do is, if I use a small symbol, small case letter cap, small I, with a subscript with a capital subscript like C, then it denotes the total current. Total current. On the other hand, if I use a capital I, subscript capital C, then this is the DC part of the current. This is the DC current. Okay. This is the steady current. And if I use small I, subscript small c, then this is the AC part of the current. AC part of the current. And therefore, I small I subscript capital C shall be equal to capital I subscript capital C plus small I subscript small c. It is this part of the current which will be of interest to us throughout the duration of the course, that is the incremental part. It is necessary for a transistor to be biased at the appropriate Q point or the operating point to be able to function as a good amplifier or other device, other application, it must be biased appropriately, and it is the incremental part of the voltages and currents which shall be of interest. Nevertheless, we shall use this terminology for the rest of the course. Okay. Yes.
Which thing are you referring as incremental?
Incremental is there is a DC current flowing into the collector. If you introduce a small AC into the base region, for example, a small base current in series with the base, then there will be a corresponding change in the collector current. It is this incremental part. Increment means over and above the DC or the quiescent or the Q point of the transistor. Okay. The other relationship that I get, if you look at this carefully, is that I sub E is the sum of I sub C and I sub B. Okay. This is by KCL. The current that leaves must be equal to the total current that comes in, and therefore I have two relations. One is I sub E is equal to I sub C plus I sub B. You must distinguish between cap and small. This I will write as capital C, and this I will write as small c. Okay. The other relation is that I sub C is equal to alpha IE plus I sub CO. This is the reverse saturation current. If I substitute for I sub E here, I get alpha I sub C plus I sub B plus I sub CO, and it is very easy to see that what I get is I sub C 1 minus alpha. If I transfer this to the left hand side, becomes equal to alpha I sub B plus I sub CO. In other words, the collector current, the relationship between collector current and the base current is that alpha by 1 minus alpha I sub B plus ICO divided by 1 minus alpha. And since alpha is very close to unity, naturally this quantity will be very large. For example, if alpha is 0.98, then I get 0.02 here, and therefore this factor will be 49. Is that correct? You can also see that 1 by 1 minus alpha can be written as 1 plus this quantity. So if I write this quantity as beta, then 1 by 1 minus alpha can be written as 1 plus beta. Agreed? Therefore, my final relationship becomes I sub C is equal to beta I sub B plus beta plus 1 I sub CO. Okay. And as you can see, you see the previous relation was I sub C equal to alpha I sub E plus I sub CO. This is the relationship between the collector current and the emitter current. This is the relationship between the collector current and the base current. And as you can see, either of them, the emitter current or the base current, controls the collector current, and this is the main feature of the solid state device called the transistor. You can also see that the slope of IC versus IE, that is DIC DIE, is simply equal to alpha, and therefore alpha is called the current amplification factor under common base connection. Alpha is the CB, common base. I sub E is the input and I sub C is the output. The base is common, so it is the CB current amplification factor. The amplification, the term amplification is unfortunate here because alpha is less than 1. Nevertheless, it is called amplification or gain, whatever it is, CB. On the other hand, DIC DIB is equal to beta, which is much greater than 1, and therefore beta is called the CE, common emitter. Emitter is common now, base is feeding, the output is the collector current, and therefore this is called the CE current amplification factor. Of the transistor. Beta is much greater than unity. As you can see, the common base connection cannot give you a current amplification, common emitter can give you a current amplification, and beta and alpha are so related. Now a typical transistor characteristic will look like this. Is the picture clear on the monitor? Okay. This is a typical transistor characteristic where what we plot is I sub C, the collector current, is in milliamperes versus VCE, that is the let me put this here. This is E, this is C, and this is the current I sub C, this is the current I sub B, okay, and this is the voltage V sub CE plus minus. Okay. What we are plotting is the collector current versus collector to emitter voltage, and as you can see, this characteristic I sub C versus VCE depends on what you inject at the base, depends on what IB is. It is controlled by the base current, and as you can see, as I increase I sub B, the collector current increases. For example, take one typical example, let us say this curve for 50 microampere. 50 microampere is the base current, and with this current a constant, if I vary VCE, then the current gradually rises like this and then becomes almost flat. Alright, it becomes almost flat, and this happens at every value of I sub B. As you go on increasing I sub B, the collector current increases, and if you look at these characteristics, these are actual characteristics of 2N222 transistor, and as you can see, the intervals, that is at equal increments of the base current 50 to 100, 100 to 150, the increment of the collector current is almost the same, which means that these curves are parallel to each other, and it is this parallelism and equal increments for equal base current increment that gives you a linear amplification. The transistor is a highly nonlinear device. It has a diode at the input, it has a diode at the output. The diode characteristics are nonlinear, but overall characteristic of the collector current versus collector to emitter voltage is such that it can be used as a linear amplifier. For example, if my operating point is somewhere here, let us say, and I increase IB by 50 microampere and I decrease IB by 50 microampere, it is the same change in the collector current, which means that there is a linear amplification. Now there are several things to be noticed, namely that for if I sub B, if there is no injection, at the base, if the base current is 0, then the collector current is approximately equal to 0, because it is the base current which controls the collector current. And you have also seen the relationship, that is I sub C is equal to beta I sub B plus I, did I introduce this term? ICO beta plus 1. This is usually called ICEO. This is a name given to it. Normally ICEO is a very small quantity. I sub CO is of the order of microamps, a few microamps. Beta plus 1 maybe typically 50. So this is of the order of 50 to 100 microamps, that's about it. On the other hand, I sub C is of the order of a milliampere or more, and therefore this term is usually negligible. So the relationship that is valid is I sub C equal to beta IB, and when this relationship is valid, we call the transistor to be working under active region. The transistor is said to be in the active region, and if you if you look at this characteristic, the active region is contributed to by the region of the characteristic in which equal increments of IB lead to equal increments of I sub C, that is these parallel lines. Naturally the rising portion of the characteristic is excluded from the active region. In other words, the active region is excluded, active region is bounded by this line. It is also bounded by this line, because if IB is 0 or negative, then the transistor does not conduct. This current that flows is only ICEO, which is tens of microamperes, all right. This is not the current that we want. We want a much larger current. So if IB is negative, then of course the collector current would be 0. If IB is 0, a small current flows, which is of no concern. So this line is called the cutoff line. When the transistor is operating under such conditions, it is said to be cut off. So I have defined an active region and a cutoff region. Obviously the active region is bounded by this line and this line. Okay? Is there a third bound? The question is there a third bound? Third bound comes because if you remember, I sub C versus VCE, while collector base junction is also a diode, a junction diode which is reverse biased, and VCE is a reverse bias, and therefore I cannot continue to increase VCE without destroying the device. There will be some point of VCE at which the current will try to rise, current will start rising very fast. In other words, the collector junction will break down, and when it breaks down, obviously this parallelism and this nice relationship between IC and IB will not be valid, and therefore the active region is bounded by the cutoff line. This line, which I shall come to in a minute, this line is called the saturation line, and the breakdown region on the third side. On the fourth side, it is bounded by what load you apply. For example, if a load is such that the load line is this, then the upper limit is this. Upper limit is this. Now what the load line is, load line, if you remember, the collector will of course be connected to a positive supply through a resistance, let us say RL or RC, call it a collector resistance, then it goes to a positive supply VCC, and therefore if this is grounded and this is VCE small v, then VCE is equal to VCC minus, this is the collector current I sub C, small I sub C, minus I sub C RC. Okay, this is very simple. The collector emitter drop is the supply minus the drop in the collector resistance, all right. This equation, when plotted on this graph, gives what is called a load line. This equation is plotted here. For example, when VCE is equal to 0, VCE is equal to 0, IC is VCC by RC. This is the point when VCE is equal to 0. On the other hand, when I sub C equal to 0, VCE equal to VCC. So here the supply can immediately be read. What is the supply here? 10 volts. Okay. So this is the load line. So the upper limit is settled by the load line, nothing else, all right. The lower limit is set by cutoff. The left hand vertical limit is set by the saturation line, and the right hand limit is set by breakdown. Bounded by these four lines, we get the active region, and this is the region of interest as far as this course is concerned. Okay. Nevertheless, we shall, through examples, we shall illustrate what happens under cutoff, what happens in saturation, and so on and so forth. But you must remember that it is this large region of the characteristic which we are concerned with, in which the lines of I sub C versus VCE for a fixed IB is a parameter now, for a fixed IB, when these are parallel, this is the region that defines our region of interest. We are not interested in the other regions. Other regions will be taken care of in the digital electronics class, or the nonlinear transistor circuits. Now we must look at, we must now explain what this line corresponds to and why do we call it a saturation line. Let's look at a typical transistor circuit. This is an NPN transistor, NPN because the arrow points out, and as I said there is an R sub C and there is a plus VCC. VCC is the positive supply, okay, and this goes to ground, this goes to ground. VCE, and this is I sub B. This voltage is VBE, okay. VBE, as you see in the active region, shall be taken as how much? 0.7 volt. If the transistor is silicon, not otherwise. If the and it is silicon transistor which we mostly use these days. We don't use any other transistor. Okay. Now, if you look at this, obviously VCE is equal to VCC minus, if this current is I sub C, minus I sub C R sub C, okay. And we also know that as we increase I sub B, the collector current I sub C increases, because I sub C is equal to beta I sub B plus ICEO. All right. Now question is, how long can we increase IB? How long can we increase, how much can we increase IB? As IB increases, IC increases, so VCE decreases, isn't that right? And the maximum I sub C that we can get from the circuit is VCC by R sub C. That is, when I sub C, when IB increases, I sub C tends to VCC by R sub C, all right, and if that happens, then that leads to V sub CE tends to 0, right? Okay. If that happens, if VCE tends to 0, this voltage tends to 0, then what will happen is VCB, that is the voltage between the collector and the base, which I can write as VCE minus VBE, agreed? VCE tends to 0 and VBE is left at 0.7, and therefore VCB becomes negative. What does it mean? If the collector base junction is negative, then the collector base junction becomes forward biased. All right. So it is this external circuit which under certain conditions can dictate the biasing of the two junctions. The emitter base junction is forward biased. If the collector base junction is also forward biased, then you see VCE tends to 0 and saturation of the current occurs. The current cannot exceed beyond this, all right. Current cannot exceed VCC by RC, and therefore this is called the saturation region. And under saturation conditions, VCE, it is found, cannot exactly reach 0. It saturates at the value 0.2 normally. So our VCE sat is equal to 0.2, of the order of 0.2, okay, VCE under saturated conditions. And you must remember the collector current cannot go beyond VCC by RC. Now what will happen if I continue to increase IB? I continue to increase IB, I sub C is saturated at VCC by RC, so this relation I sub C equal to beta IB shall no longer be valid, okay, shall no longer be valid, because I sub C has reached a saturation. In fact, one of the tests for saturation is that I sub C by I sub B shall be less than beta. This is the test for saturation. When when the base current is very large, that the collector is not able to cope with it in a linear manner, this is the onset of saturation. And when saturation occurs, the base emitter voltage VBE also has a limit, because after all you remember that the diode characteristic is like this. Okay, it cannot go beyond a certain voltage, and what we do is, now we must we must be careful. What we do is, as I said, for making a model we take this as 0.7 volt. That is, the linear approximation to the characteristic cuts the voltage axis at 0.7. So we take VBE, note this carefully, VBE active as equal to 0.7 volt. VBE active is 0.7. Then in describing transistor action, we must also take care of the voltage at which the diode just starts to conduct, because there are circuits in which the regeneration is automatic, digital circuits, logic circuits for example, and the voltage at which the emitter base junction just starts to conduct is called the VBE cut in. That is, it was cut off earlier, now it is cut in. This is taken as 0.5 volt. These are gross figures used for silicon transistors. There may be small variations. For example, instead of 0.7, the actual value could be 0.65. Instead of 0.5, actual value could be 0.6. And you see, when the transistor is saturated, VB is set, when the transistor is saturated, this voltage after all cannot exceed a certain value, and this value is taken as 0.8 volt. VBE saturated. So under saturated condition of a transistor, VCE set is 0.2, VBE set is 0.8, VBE active is 0.7, and VBE cut in is 0.5. These figures you must remember. In an actual transistor case, there may be small variations. This will be specified by the manufacturers, but if nothing is specified, these are very good figures to take, and designs based on this. After all, no design made on paper is going to work in the laboratory. You will have to make adjustments, and therefore these are good figures to start with. You design the circuit, wear it up, and then you make small adjustments here and there to get what you want. Okay, that's a fact of life. So you understand what I mean by saturation. It's very important to understand. This is the saturation line, and saturation occurs when VCE is very small, tends to 0, and this value is taken as 0.2. In the ideal case, we will not take this line as inclined. In the ideal case, we will take it to be vertical. Alright, we will take it to be vertical, parallel to the I sub C axis, starting at 0.2 volt. Okay. Now therefore, one more thing that I want to point out in connection with this. If you notice carefully, these lines are not absolutely parallel to the VCE axis. They are slightly inclined. It's not quite saturated. There is a small increase in collector current as you increase VCE. All of these lines, in fact, you see that the difference here is not the same as the difference here. So there is a slight inclination, and this happens because with increase of VCE, the base region becomes thinner and thinner. The depletion region extends right into the base, and it becomes thinner and thinner, and this was first discovered by a gentleman called Early, E-A-R-L-Y, and this is why this is called Early effect. It was discovered very early, in fact, but it has not been taken care of so far. How to take care of this is the following. Suppose you have characteristics like this. I am showing an exaggerated picture. I am showing this inclination in an exaggerated manner. Now if I extend it was also shown by Early. It is a very interesting and very elegant geometrical figure. It was shown by Early that if I extend this on the left hand side, this is the I sub c versus VCE characteristic. Okay. And if I extend all of these lines to the back, it turns out that they meet approximately at the same point. It's a very interesting discovery. So this point, the value of the voltage is the VCE axis, it is a negative voltage. The value of the voltage was called V sub A, and it is called the Early voltage. The discovery is that not only these curves are not parallel to the VCE axis, but if you extend them backwards, then they meet at a certain point on the VCE axis, and the value of the voltage here, in order to honor Early, is called the Early voltage. We should have used V sub capital E, because E is the first letter in Early, but V sub E is unfortunately used for emitter voltage, and therefore we end up with the next letter A. Is that clear? VA is the Early voltage, and typically VA is of the order of minus 30 to minus 150 volt. Okay, and you see that this current, this ratio VA by I sub C at a particular operating point is the dimension of a resistance, and this is denoted by R0 and is called the Early resistance. Early resistance. This resistance is useful in the transistor modeling. It is not only the ratio of VA to IC, but it is also the slope of this line. Okay, the slope of this line is R0. Is that clear? The reciprocal of this slope. Don't agree with me on all counts. It's dVCE over dIC. So this resistance would be useful in the AC modeling of the transistor. Okay, now with this no, I have to do something else. This is as far as the collector based junction is concerned. Okay, let's look at the emitter based junction, that is the input junction. In the input junction, if I take the ratio dVBE dIB at the Q point, the emitter based junction is a diode, and therefore this slope would be given by, if you remember, KT by Q I sub B, KT by Q I sub B. This resistance is the resistance appearing between base and emitter, and therefore it is denoted by RBE, between base and emitter. Note these symbols. This is small b, small e, which means that this is the incremental resistance. Okay, incremental resistance. Now this is KT by QIE, and you know KT by Q is approximately 26 millivolt. So this is of the order of 26 millivolt divided by I sub B, and I sub B, as you know, is given by I sub E divided by beta plus 1, beta plus 1. So this is beta plus 1 times 26 millivolt divided by I sub E or I sub C, if you so desire, because they are approximately equal. They differ only by I sub CO. Now this resistance obviously is the resistance which is faced at the emitter terminal, and therefore this is denoted by R sub E at the emitter terminal, as if I sub E is the input current to the diode. Then this is the resistance that you face. You see, the difference of resistance RBE and RE occurs because the reference current in one case is IB and the reference current in the other case is I sub E. They differ by a factor of beta, actually beta plus 1, but beta is very large, so beta plus 1 is okay. Therefore, in AC modeling of a transistor, between the base and the emitter you need a resistance RBE. Okay. In addition, however thin the base may be, any electron current, any current that has to come to the base region, that has to come to the base, let's say this is NPN, any current that has to come to the base has to traverse this width of the base. Okay. The physical fabrication, physical parameters are such that the width of the base has to be traversed by any current that comes here, and the resistance of this thin base region comes into effect, and this resistance is called R sub B and is called the base spreading resistance. Now conceptually this is the matter, this is the that any current coming to the terminal, base terminal, must go through the width of the base, and that resistance will have to come into effect, whereas RBE is not a physical resistance of a material, it is not rho L by A, it is the resistance occurring because of the junction, because of the semiconductor junction, because of the semiconductor junction diode, and therefore if base is this terminal and emitter is this terminal, from base to emitter it's not simply RBE, I am talking of AC, it first comes with R sub B, that is the physical resistance of the base called the base spreading resistance, and then from this point to emitter is RBE, and therefore between base and emitter there are two resistances in series. One is due to the physical resistance of the base region, and the other is the diode resistance, diode dynamic resistance RBE, and for reasons to be made clear later and for simplicity and for uniformity we shall denote this resistance by Rx. In our circuit modeling, in the analysis of transistor and all that, and this resistance we will call as R pi. To simplify notations, this is Rx, this is R pi, and this hypothetical node, this hypothetical node is called the internal base and is denoted by B prime. This is called the internal base and is denoted by B prime. So some textbooks, instead of Rx they use RBB prime, that is between the actual base terminal, external base terminal, and the internal hypothetical base RBB prime, and sometimes textbooks use, instead of R pi they use RB prime E. Now RB prime E is of the order of a K, 1K, whereas the base spreading resistance is usually a very small quantity of the order of 100 ohms. There is at least a 1 order magnitude difference between Rx and R pi, and you know in electrical engineering if any quantity is greater by another any quantity is greater than another quantity by a factor of 10, we say the former quantity is much greater. Okay, much greater sign, A much greater than means, much greater than B means that A is greater than 10 times B. So Rx is usually taken as much less than R pi, and in circuit modeling, to keep life simple, we usually ignore Rx. Not always, there are situations when Rx cannot be ignored and we have to take account of Rx.
Excuse me, sir.
Yes.
So how about the emitter resistance? Is it much smaller than the other resistances?
This is the resistance.
So RE. The RE.
RE is, the relationship between RE and R pi is obvious. If it is a common base circuit, if the emitter is the input and base is common, then the resistance that will come between emitter and base would be RE, and this will be beta plus 1 times R pi. Okay, so Re and R pi are very simply related.
So what about the physical resistance of the ohmic resistance? The
Physical
part of
resistance, pardon me?
physical resistance of the emitter. Like you call the physical resistance of the base. So what about the physical resistance of the emitter?
Well, that doesn't come into consideration because this is already taken care of by the current voltage relationships of the diode. You see, in the base it matters because it's a very thin region and much less heavily doped than the emitter region. Emitter region is very heavily doped because it has to emit. Now, if you heavily dope, if you make the doping as N plus, and you know the number of carriers available is very large. If the number of carriers is very large, then the resistance goes to 0. It can conduct very well and therefore the emitter bulk does not offer a substantial resistance. On the other hand, the collector bulk does offer a resistance. This we have already explained, R0, small r0, which happens because of the early effect, because it's less heavily doped than the emitter. So the emitter region does not contribute to a bulk resistance. Is the point clear? Okay. Now the DC model therefore that we shall be using for a common emitter transistor would look like this. We have a base, we have a collector and we have an emitter. Between the base and the emitter, DC model, what we have is a diode, okay, and between, alright, let me extend this, between the collector and the emitter we have a current. If this current is I sub B, then the collector current consists of two components. One is beta I sub B and the other is ICO, and this is my I sub C. This is the DC model that we shall be using for a common emitter bipolar junction transistor. If you so desire, this diode can be replaced by an ideal diode. You must write ideal, and what else? A 0.7 volt battery. Okay, a 0.7 volt battery. That is as far as DC is concerned. When it is AC, we shall replace this. We shall include. We can replace the ideal diode by a short circuit, the 0.7 volt by a short circuit, and we shall include a resistance which is equal to R pi. Okay, agreed? Now, as far as the
Excuse me, sir.
yeah,
So this is a DC model, then why are we taking the incremental value of IB? We should take only the DC value.
we have taken the DC value.
That symbol used is like
That is only for AC. That is when there is an increment here. As far as that increment is concerned, suppose, okay, I get your point. Suppose IB equal to IB plus small ib, then as far as if small ib is 0, then this is the model. If small ib is there, then in addition, because both of these will be short circuits, in addition you have to consider a small resistance which is the incremental resistance. Okay. As far as the output circuit is concerned, well, for DC this is the circuit, but for AC, which will disappear? Will both of them disappear? This will disappear, but beta IB shall remain because beta is the slope DIC DIB. Agreed? Okay. And in addition, for AC, there shall occur a resistance from collector to emitter, and this resistance is the early resistance. Is that okay? So AC model would be, if I draw it, AC model would be R pi if I ignore Rx, or you can, if you don't want to ignore Rx, then you put Rx in series, and you have beta IB, this is IB in parallel with R0. This is the AC model, provided the transistor is at the appropriate operating point. Okay, we can take a quick example. to illustrate this, and this example is a common emitter transistor, and a resistance 27K in series with the base, then a battery of plus 2 volt, this supplies the base current, and we have a resistance of 500 ohm in series with a plus 10 volt, and this is grounded. What this means is that there is a battery 10 volt here, the negative terminal of which is grounded. Similarly, here there is a battery of plus 2, the negative terminal is grounded. Okay. The question is to find out VCE. Now I have used capital V sub CE, which means that the DC operating point, VCE and I sub C. It is given that VBE is equal to 0.65 volt, not exactly 0.7, slightly less than 0.7, 0.65 volt. It is given that beta is equal to 150, a large value, and that ICEO can be ignored. ICEO tends to 0. The question is to find VCE and IC. Alright. To solve this problem, what you do is you first find out I sub B, capital I sub B, DC conditions. Okay. Capital I sub B obviously would be equal to 2 volt minus this voltage minus 0.65 divided by 27K, and this comes out as 50 microamps. If you know this, then you can find out I sub C. I sub C is beta times, so 150 multiplied by 50 microampere, this is equal to 7.5 milliamps. Alright, and you know I sub C, I must use capital I sub C, and therefore you can find out VCE. That would be equal to VCC 10 minus 7.5 milliamps multiplied by 500 ohms, and this comes as 6.25 volt. We have solved the problem. Suppose a question. Suppose this voltage came out as 0.2. What would have been your conclusion?
Saturation.
That the transistor is in saturation. If it is anywhere close to 0.2, even 0.3 or 0.4, you must look upon all this calculation with suspicion, because VCE set is not exactly 0.2, it might go on the other side. But if it is 0.1, then you definitely know that it is in saturation. If it is in saturation, then obviously this, utilizing this relationship is suspect. You cannot use this, IC equal to beta times IB. Okay, we will continue a second part of this problem tomorrow.